So this is the first session on rigid body kinematics. Okay. Before this chapter, 59 videos on relative velocity have been discussed, have been made. So now in this chapter, in this next topic, we take up the first session on rigid body kinematics. Okay. So first, what I'll do, I'll outline the topics which have to be covered in this chapter. Okay. Then I'll take up one by one all the chapters of this topics of this chapter. Okay. So first I'll write what this is all about. So in this first session on rigid body kinematics, we will discuss the kinematics of rotating rigid bodies in plane motion. Okay, this is what we are going to discuss. Kinematics of rotating rigid bodies. Kinematics of rigid bodies in plane rotation. Kinematics of rigid bodies in plane rotation. Kinematics of rigid bodies in plane motion, plane rotation. This is what we are going to take up in this chapter. Okay. That is, we'll simply we'll say that we'll take up the kinematics of rigid bodies in rotation. Okay. First, what we'll do, I'll outline the topics which will be taken up in this chapter. Okay. So in this entire chapter on rigid body kinematics will be divided into 4 topics. I'll mention the topics A, B, C, D, and D. Topic A is this: angular velocity calculation of rigid body in plane rotation. In plane rotation with respect to some given frame F. Okay. Of angular velocity calculation of rigid body in plane rotation. Then in sub case B, we'll take up the velocity calculation of a rotating rigid body. Velocity calculation of a rotating rigid body. Then we'll take up acceleration calculation of rotating rigid body. Acceleration calculation of rotating rigid body. And lastly, we will take up the chapter on instantaneous center of rotation, that is briefly stated as IC. Instantaneous center of rotation. Instantaneous center of rotation, or simply IC. Okay. These are the 4 topics which have to be taken up in this chapter. So first, what we'll do, we'll take up the sub case A. This we'll discuss first, this one. Okay. So I'll grab all it. Okay. So first, what I'll do, I'll define what is meant by plane rotation. Okay. I'll define what is meant by plane rotation. So First we define plane motion. Okay. What do you mean by plane motion of rigid body M with respect to some given frame F? Suppose F is some reference frame. Okay. M is some other rigid body or some other reference frame which is moving in plane motion with respect to F. So suppose M undergoes plane motion of M. Suppose M undergoes plane motion with respect to F. Suppose M undergoes plane motion with respect to F. What does this plane motion mean? Plane motion means all the material points of M move in plane trajectories in parallel planes as seen from frame F. That is what is meant by plane motion. Okay. So we say that M is said to undergo plane motion with respect to F if all the real and imaginary locations of M move in plane trajectories in parallel planes. Move in plane trajectories parallel planes with respect to F. So M is said to undergo plane motion with respect to frame F if all the real and imaginary locations of M move in plane trajectories in parallel planes as seen from frame F. That is what is meant by plane motion. Okay. So now plane motion can again be divided into two types: plane translation and plane rotation. Okay. So plane motion can be categorized into two subtypes. One is plane translation and next is plane rotation. Plane translation and plane rotation. Okay. Like that always. Okay. Now plane translation has been fully discussed completely in the chapter on relative velocity. I just state it here for completeness. It is not going to be used now. This has already been discussed. Plane translation means M is said to undergo plane translation with respect to F if all the locations of M move in identical plane curves. They move in identical plane curves. That is what is meant by plane translation or 2D translation. Okay. So this has fully been discussed in the chapter on relative velocity. In the first few videos of relative velocity, you will get all these things in detail. Plane translation, everything. Okay. So this has already been discussed. Now we will take up this case, plane rotation. So plane rotation definition is same as was given for plane motion. Okay. All the material points of M move in plane trajectories in parallel planes. And the body is rotating simultaneously also. That is what is meant by plane rotation. Okay. So how do we finally define plane rotation? M is said to undergo plane rotation with respect to F if M rotates in such a way as seen from F so that all the material points of M move in plane trajectories in parallel planes. That is what is the complete definition of plane rotation. Okay. So plane rotation will define in this way. Plane rotation of M with respect to F. So how do you define it? Plane rotation of M with respect to F will be defined in this way. M rotates as seen from F. Now what is rotation? This has also been discussed fully in the all the videos of relative velocity. In the first video 1 to 5, first to 5th video of relative velocity, you will get all these things in detail, you will get there, okay. You can just go to the videos on relative velocity, first 5 videos, okay. They will get all these things, okay, fine. I am just stating it here, this is already been discussed. So plane rotation of M with respect to F, meaning M rotates with respect to F in such a way that M rotates with respect to F in such a way that all the real and imaginary locations of M move in plane trajectories in parallel planes. As seen from F. So M rotates with respect to F in such a way that all the real and imaginary locations of M move in plane trajectories in parallel planes as seen from F. That is what is meant by plane rotation of M with respect to F. Okay. Now first thing we must note, what is meant by real and imaginary location. So this is also been discussed fully in the first few videos of relative velocity. In the 7th video of relative velocity, you will get all these things, real and imaginary locations of M. If you go there, you will get all the details, okay. And so this I will not explain again, okay. So what is meant by plane trajectory? Plane trajectory meaning a plane curve, a trajectory or curve in which all its points lie in one plane. That's called a plane trajectory. Circle is an example of plane trajectory. Ellipse, example of plane trajectory. Hyperbola, example of plane trajectory. Parabola, example of plane trajectory. Okay. Helical motion, it's not a plane trajectory, it's a 3D curve. Okay. So this is what is meant by plane trajectories. Plane trajectory is simply a curve whose all of its points are coplanar. They lie in the same plane. Okay. In parallel planes, so each of these parallel planes, this will be referred to as the base plane. This parallel plane will be referred to as what? Base plane. This will term it as the base plane. Now we will take up some examples on plane motion. Okay, fine. This I'll rub it, okay? So I'll take up some examples of plane motion, okay? Examples on plane rotation. Examples on plane rotation, okay? First example. Suppose that instead of frame F we have the ground frame G. Instead of F we have the ground frame G, okay? So now, for example, see, this is a fixed ceiling, okay? This is a rod, pendulum rod, say. You know, you are familiar with the word pendulum, okay? This is the hinge point. This is the pivoted. Rod is pivoted about this point. It can rotate about this point, okay? So this is the pivot. Now the rod swings like this. The rod, what do we do? We take the rod, we bring the rod till here, say, and then release it. So this, what will happen? It will begin to move like this, see, like this. So this rod undergoes plane motion with respect to ground. Why? Because all the material points of the rod move in this vertical plane. They move in a family of parallel planes which are parallel to the plane of this board. In fact, all of its material points move in circles whose planes are lying in this vertical plane. So it's an example of plane motion as seen from ground. Okay. This pendulum rod, as it swings like this this undergoes plane motion with respect to ground. All of its material points move in plane trajectories which lie in this family of vertical planes containing parallel to the plane of the board. So that is an example of plane motion as seen from ground. Okay. I'll take another example. Suppose we have an elevator like this. A rod is swinging here. Okay. It is pivoted about this point. This is the pivot. This is the pivot. Elevator moves upward and the pendulum rod swings like this. So this rod undergoes plane motion as seen from ground. Because all of its material points move in plane trajectories which lie in the family of parallel planes parallel to the plane of this board. So this is an example of plane motion as seen from ground. This is also a plane motion as seen from elevator. In elevator also this undergoes plane motion. Okay, so it's undergoing plane motion as seen from ground also, and is undergoing plane motion as seen from elevator also. In both the frames it is undergoing a plane motion. Alright, fine. Then third example. Third example is this. Suppose it's a fixed ceiling. Okay. Again, instead of F we have the ground frame. Instead of F we have the ground frame. This is a fixed ceiling. This is a fixed what? Ceiling. Fixed ceiling. Okay. This is a fixed ceiling. Rod is pivoted here. It is free to move like a conical pendulum. You understand what is meant by conical pendulum? Like this. This is a fixed ceiling. This is a rod. It is pivoted here flexibly. Rod moves like this. This is said to undergo a conical pendulum motion as seen from ground. All this rod moves on the curved surface of a cone whose axis is vertical and whose apex lies at the pivot like this. This is an example of plane motion as seen from ground because all of its material points move in horizontal circles. I'll draw the diagram also. This is the rod, okay? This flexibly joined here, pivot. Rod is moving like a conical pendulum like this. Rod moves in a conical pendulum in this fashion. So this rod undergoes plane motion as seen from ground. Why? Because take any material point of the rod. This moves in a horizontal circle which lies in this plane, horizontal plane. Take any other material point of the rod. This also moves in a horizontal circle. So all its material points move in circular motions whose planes are horizontal. They lie parallel to these horizontal planes. So these are the base planes. This any plane containing the circular motion of the material point of the rod, that's a base plane. That's a base plane. Okay, fine. In this example also, first example, rod is swinging like this. This was the base plane. These are the family of parallel base planes in which the material points of the rod move. And imaginary points also. Imaginary points also, they have been fully discussed in the 7th video on relative velocity. You can go there and check it, okay? You can verify it there also, okay? Fine. You can check it there also. Confirm it there, okay? I'll take another example. Consider a vehicle. See, this vehicle is moving away, moving rightward, and this wheel, I'll draw this wheel here, okay? See, like this. This is the wheel. This is the center of the wheel. This center moves ahead, and the wheel moves like this. Like this. So this wheel undergoes plane motion as seen from ground. Why? Because all the material points of him move in plane paths which are contained in this vertical plane, parallel to the plane of the board. So this example of this wheel moving with respect to ground is an example of a plane motion. And which are the base planes? Family of parallel planes containing the trajectories of the motion of its material point. They are the base plane. These are the base planes. Okay. So this example of this motion moving wheel with respect to ground is an example of plane motion. That's also a plane motion of wheel with respect to ground. Alright, fine. I'll wrap this, okay? So, one more thing I'll take. It is not necessary that if a body undergoes plane motion with respect to some frame F, then also with respect to some other frame it also undergoes plane motion. No. That is, plane motion is an example of relative, it's in relative sense. It's not absolute. It's not that if M undergoes plane motion with respect to F, then M also undergoes plane motion with respect to some other frame F1. No. I'll just take another example to demonstrate this concept. See this one. Suppose we have an elevator moving upward with respect to ground. Instead of elevator we write E. Instead of F we have ground frame. Okay. This is a rod which is pivoted here flexibly. Rod moves like a conical pendulum with respect to elevator. And elevator moves upward with respect to ground. Now with respect to elevator, the rod moves like a conical pendulum. So with respect to elevator, the motion of rod is like that of a conical pendulum. But as seen from ground, motion of this rod is not a plane motion. Why? Because see what happens. This elevator moves upward. This pivot also moves upward with respect to ground. And with respect to elevator, the rod moves like this, like a conical pendulum. Then as seen from ground, suppose we take any material point of this rod, this point say. As seen from ground, this point will not move in a plane motion. It will undergo in a 3D motion. Like this. Like a helical path, spring. So any of its material points do not move in plane paths, plane curves as seen from ground. So as seen from ground, motion of this rod is not a plane motion. But as seen from elevator, motion of this rod is an example of plane motion. Okay. So this demonstrates that plane motion is a relative concept. A body M might undergo plane motion with respect to some frame F1, but simultaneously it need not undergo plane motion with some other frame with respect to some other frame F2. Okay. So this is plane motion is an example of, it's just in a relative sense, it's not absolute. Fine? Alright. Now I'll wrap this, okay? Now, first what we'll do, we'll take up the angular velocity calculation of rigid body M in plane motion with respect to F. So suppose M is a rigid body which undergoes plane rotation with respect to F. Now, instead of using the word plane rotation, I'll use plane motion. But in this case, whenever I talk of plane motion, it will imply that it's case of plane rotation. Okay. So suppose M undergoes plane motion with respect to F. M undergoes plane motion with respect to F. Okay. So, as I've said just now, this means plane rotation. So let omega be the angular velocity of M with respect to F at certain instant t. At certain instant what? T. So omega is what? Angular velocity is the rate of change of orientation of M as seen from F. That is what is angular velocity. First of all, angular velocity is a vector quantity. If it is a vector quantity, it must have a magnitude, it must have a direction. Magnitude of vector omega is this, we should denote it simply like this. This is the angular speed angular speed of m with respect to f at time t. And if it is a vector, it should also have a direction. Now, direction of omega is always perpendicular to the base plane. Okay, so omega is, direction of vector omega is perpendicular to the base plane. Direction of omega is perpendicular to the base plane. Direction of omega is perpendicular to the base plane, and its magnitude is called the angular speed of m with respect to f at time t. And direction of omega is perpendicular to the base plane. Okay. Now, suppose this board is the base plane. Now, vector omega, direction of omega is perpendicular to base plane. Now, vector omega can either be directed in this way or in this way. In both the cases, it is perpendicular to the base plane. Now, which one do I choose, this one or this one? So, that is decided by the right hand thumb rule. If the sense of, suppose this is a frame F, suppose this is frame F, suppose the sense of rotation of omega is clockwise, that is, sense of angular velocity is clockwise, then direction of omega will be normally into the base plane. This is simply by right hand thumb rule. If the sense of omega is clockwise, sense of omega is what? Clockwise. Then direction of omega is perpendicularly into the plane of the board, that is perpendicularly into the base plane. So this is the direction of omega, and this cross implies perpendicularly into. Okay. And if sense of omega is anti-clockwise, then direction of omega is normally out of the base plane, that is in this direction, dot. Okay. So sense and direction of omega are related to each other by the right hand thumb rule. Sense and direction of omega are related to each other by the right hand thumb rule. Okay. If sense of omega is clockwise, so what we do? How do we decide the direction of omega given its sense? We take the right hand, we fold the first 4 fingers of right hand along the sense of omega, keeping the thumb of right hand straight. The direction of straight thumb of right hand gives the direction of vector omega. Alright. So, if omega is clockwise, the direction of omega is normally into the base plane. If direction of sense of omega is anti-clockwise, then direction of omega is normally out of the base plane. So, this is the two aspects. Alright. So, sense of omega and direction of omega, these are the two different sense and direction of omega. They are two aspects of omega. So, sense means clockwise, anti-clockwise. Body rotates like this, it's anti-clockwise rotation. Body rotates like this, it's anti-clockwise rotation. If body rotates like this, it's a clockwise rotation. If body rotates like this, it's anti-clockwise rotation. For clockwise rotation, direction of omega is normally into the plane of the board. For anti-clockwise rotation, direction of omega is normally out of the plane of the board, normally out of the base plane. Alright, so these are the two aspects of vector omega. Alright. Now, I'll just state one more thing. Angular velocity of a rotating rigid body m depends on the frame of reference. Just as velocity of moving point depends on the frame of reference, so angular velocity of a rotating rigid body m also depends on the frame of reference. Proof is statement is something like this. Suppose 1, 2 and 3 are 3 rigid bodies. 1, 2 and 3, they are 3 rigid bodies. I just write this one, 1, 2 and 3. They are the 3 rigid bodies. Angular velocity of body 3 with respect to body 1 is equal to angular velocity of body 3 with respect to body 2 plus angular velocity of body 2 with respect to body 1. This is the relation for angular velocity of angular velocity between 3 different bodies. So omega 3.1 is the angular velocity of 3 with respect to 1. Omega 3.2 is the angular velocity of 3 with respect to 2. Omega 2.1 is the angular velocity of 2 with respect to 1. If we add these two, we get this. This relation you must remember, okay? As we define omega, we also define beta. Angular acceleration angular acceleration. That is simply the derivative of angular velocity of m with respect to f at time t as seen from frame f. This is the angular acceleration of m with respect to f. Time rate of change of angular velocity of m with respect to f at time t. That is the angular acceleration of m with respect to f. Okay, fine. So, in this first session on rigid body kinematics, first I have stated which topics will take up. What the first I have told you what this is all about. First session. Then I stated all the 4 topics which will be taken up in this chapter. Then I said what is meant by plane motion. This can be divided into 2 types: plane rotation, plane translation. Plane translation also I defined as discussed in videos on relative velocity. Then plane rotation I defined it. Also, I took up the case examples on plane rotation. Then I talked about angular velocity of m with respect to f. It has a magnitude, it's a vector, it has magnitude, direction. Magnitude is called the angular speed. Then there are 2 aspects of omega: sense and direction of omega. Sense and direction of omega are related to each other by the right hand thumb rule. For clockwise omega, direction is normally into the base plane. Anti-clockwise omega, direction is normally out of the base plane. Then I said that angular velocity depends on the frame of reference. They are related by this formula. Then I said angular acceleration, what is it? I defined it. Now finally one more thing I will state which is very important. How do we formally define plane motion in mathematical sense? Definition of plane motion in mathematical sense. See, plane motion in mathematical sense will be defined in this way. M is said to undergo plane motion with respect to f. Again, in this I mean plane rotation. Okay, if omega of m with respect to f is perpendicular to velocities of all its real and imaginary locations of m, velocities of all the real and imaginary locations of what? M. So if m undergoes plane motion with respect to f, then at any instant of time, angular velocity of m with respect to f is perpendicular to velocities of all the real and imaginary locations of m with respect to f. This is the precise definition of plane motion in a mathematical sense. It's true both ways. If m undergoes plane motion with respect to f, then at any instant of time, angular velocity of m with respect to f, that is vector omega, is perpendicular to velocities of all the real and imaginary locations of m with respect to f. And converse is also true. If vector omega is perpendicular to velocities of all the real and imaginary locations of m with respect to f, then m undergoes plane motion with respect to f. It's true both ways. Fine. This is the exact definition of plane motion in terms of velocity and linear velocities. Okay. So if m undergoes plane motion with respect to f, then omega is perpendicular to velocities of all the real and imaginary locations of m with respect to f. And converse is also true. Okay. This is the first session on the rigid body kinematics. This I fully explained. Now in second session on this rigid body kinematics, I'll take up the angular velocity calculation by 2 different methods. Okay. So I close it here. Alright. Fine.